your major?
I'm in electrical engineering, and I work in the electronics lab.
I'm Greg. I'm in computer science, and I work with Jim Regier.
I'm Matt. I'm in computer science. I work with Yannis Alamonos.
Hi, I'm Felix. I work with Dan Betts in biology, and I'm in the neuroscience and cognitive science program.
Yeah, I'm Cal. I'm in the biophysics program. I work in Garrigan and Popoyan's lab.
So the goal here is to give you sort of a high-level view of what machine learning is, how it can be useful, and specifically talk a little bit about Keras, which is a neural net library. So we're not going to get too far into the details about things like, which specific neural networks to use in certain situations, but we're going to give you an idea of what they are, how they can be useful, and the steps that are involved with preparing data, training models, and using them for things like classification.
So, what is machine learning? Obviously, since we have a pretty good turnout, people think machine learning is useful, and hopefully you have some idea of what's going to happen today. Right? But just to go over it, machine learning at its most basic is the practice of using algorithms to parse data, learn from it, and then make a determination or prediction about something in the world. So it's kind of a broad and vague field that pulls in a lot of different people from other STEM fields, and even outside of STEM, because it's a really powerful tool to analyze and interpret data. So there's two really broad categories. One is supervised machine learning, in which you already sort of have an input and an output, and you want your machine learning algorithm to figure out the relationship between them so that you can put in now novel inputs and figure out where the output should be. So that would be an example of classification, which is all the way to the left, where let's say you have a bunch of apples and oranges, and you tell your model to figure out like how to map, let's say, an image to an apple and orange, and then you put in a novel input and see if your algorithm can figure out what it is, or what it should be. And then a regression model would be something similar, but with continuous data rather than like discrete categories. So unsupervised machine learning, you don't already have this predefined input and output. Instead, you have a bunch of data, and you want to either do clustering or anomaly detection with it. So clustering is you already have some data, and you want to figure out what are the categories within this data. And there are like many ways to do that. And anomaly detection is pretty self-explanatory. You have a data set, and you want to see like where roughly is, let's say, the center, or what is like the good data, and what is the data that is like an outlier and maybe shouldn't be used for your further analysis. So one famous example of unsupervised machine learning and the data set that people use for a lot is this iris flower data set, where these 3 flowers on the right are actually different species, and it's really hard, as you can tell, to tell them apart if you don't already know very specifically what the differences are, and you pretty much have to be a botanist to look very closely. But if you feed a bunch of these images into a machine learning algorithm, it can measure these specific parameters like petal shape and size, and you can create different clusters based on that and use them to tell 3 species apart.
So this is another example of machine learning that actually comes from our lab. My lab mate, Ervin, made this figure. This is another example of unsupervised learning. So basically what he did was look at the morphology of these actin bundles under different concentrations of myosin motors and cross-linkers. So moving across the right, we have increasing myosin, and up we have increasing cross-linkers. And you can see there's like a wide variability of these resulting morphologies. And a natural question would be, what's like the most natural set of categories to describe this wide variability of these shapes? And so he used a machine learning algorithm called hierarchical agglomerative clustering, which basically just creates successive partitions of your data, where each partition is kind of trying to maximize the intergroup similarity and the intergroup dissimilarity. And so you can do that, and the result is this tree structure called a dendrogram. And the leaves of that would just be original data. And then at a certain point, you can look at a slice of that tree and see these are kind of the reasonable clusters that can describe the categories for this data. And then using your knowledge, you can then interpret those clusters and say that these blue ones are these after-like structures, and the red ones are these like fused bundles, and the green ones are these compact bundles. And so this algorithm is able to like learn the most natural set of partitions to describe this data, which you were then able to interpret. Okay, so just kind of general considerations for when you want to use machine learning. First of all, your data should be very plentiful and representative of all the categories that you want to try to analyze. Otherwise, it just probably won't work very well. And the problem should be very complex. So try to imagine like designing an algorithm that could look at the image and tell you where in the image it faces. I mean, trying to do that by hand would be like almost impossible. And so if you can't like do that by hand, then a good approach is to have a machine train on data and develop its own rules to do that. Also, if predictive accuracy is like the most important thing for your problem, then machine learning is a good approach. So like if you're trying to sell a spam filter, then the difference between like 99.6 and 99.9% accuracy is going to be important for you. Even if you don't really care like what's happening, you really just want to hit that high mark. So machine learning can be very accurate, but it's not very interpretable. So if you care about things like causality, machine learning will just kind of exploit correlations in your data to get your results. So if it's important to you to like understand what's going on, then you might want to try a different approach. So when not to use it is when you just don't have very high quality data, it's very noisy and there's not a lot of it, then it probably won't work very well. If the problem is very simple, then machine learning is likely going to be overkill, and you get more better interpretable results if you just do another method. And yeah, if interpretability is important, then probably not very good too. Okay, so if you want to do machine learning, then this is a list, just a short list of some tools that are out there. So these are all available, some are open source, some are not. And they kind of do some of the heavy lifting of machine learning for you. So the first one is Scikit-Learn. That is implemented in Python. It's a Python module. I've used this one. It's pretty easy to use. It's open source, which is nice. And it does a lot of different machine learning methods like clustering and generates trees for you and some neural network stuff. But it's not particularly deep. You can't do, for example, convolutional neural nets or any kind of deep learning. So if you want to like really get into that kind of stuff, then it's probably not your best bet. There's also MATLAB, which has some library functions, and there's some toolboxes, particularly this neural networks toolbox. This has some light capabilities, and as kind of a bonus, you could use MATLAB, which I think a lot of people are pretty comfortable with. From what I can tell, it's about the same level of depth as Keras, which we'll talk about today, but it's not open source, so you have to pay for MATLAB. But it seems like a good option from what I can tell, and you can do deep learning with that. Then there's also Apache Mahout with the Hadoop language. I'm not super familiar with this, but from what I can tell, it's good for like very large-scale projects. If you have like big data, then you can use like distributed storage and processing, like on a team project, and kind of analyze these large sets of data more efficiently. And then lastly, we have a Tensorflow, which you can download as a library with C++ and include in your projects there. And it's also a Python module that you can import. So this is Google's flagship deep learning platform. You can build networks with pretty low-level control, but if you're just kind of getting started, then it's kind of difficult to use, just because we have so much kind of flexibility. So it can be cumbersome, but that's where Keras comes in, which is a wrapper for TensorFlow, and kind of takes away some of the heavy lifting, but still allows you to have some kind of good control over building your networks. Okay. So just some other machine learning concepts. You need to think about the distinction between underfitting and overfitting. So in this simple regression example, we have these 10 data points that we can fit either. So fitting, this comes down to how many free parameters we give our model. So in the underfitting example, we just give one free parameter, and we see that it just finds the average of these points. And so that performs pretty poorly even on the training data that we give it. At the other extreme, we have overfitting. So we give it 10 free parameters, and we see that we can hit actually every one of these points exactly. But you can imagine that if you just drew like one more data from your population, odds are it won't be like anywhere near this right curve. So basically what happens is just memorize the training set and just really learn from it. So you want like the middle ground where you're not completely hitting all data points, but you generalize more, you generalize better. And just one other way to think about this is in terms of bias and variance. So bias is basically the accuracy of the model over the training data. And variance is how much the model will change if you use a different set of training data, so a different sample from your population. So coming back to this picture, we see that this blue curve has very high bias because it's not very accurate on the data. But you can imagine that if we did a different sample, we'd probably find a similar average, so its variance is low. Whereas the red curve has very low bias because it hits all these points exactly. But if we had a different set of training data, there's like no way that we would get the same curve. So it has, in general, if you have high bias and low variance, then you're probably underfitting. And if you have low bias and high variance, then you probably are overfitting your data.
Okay, so another really important consideration for when you're building your model is feature engineering and selection. So what you want to do is, to save time and energy, a lot of times you want to transfer your raw data, which might be like huge. Let's say you have a bunch of photos or you have sound clips. And just instead of feeding those directly into your model, you can pick out important features. You can pick out important features of those and use those as your input. It just kind of reduces the amount of stuff that you have to process. But you have to figure out which are the ones that are important and which ones are either redundant or you're just going to mess up your number. So you can do it just with what you know, like things about image processing, like faces should have a general face shape and kind of intuitively figure out what that is. Or you can start with images, or like start with your huge data set and then figure out as you go what are the things that are actually important, what are the things that are not important, and then sort of go back and pick them out later. So yeah, if you use deep learning, you can kind of skip that, like I said, and do that. So to start talking about what we're actually going to do today in your tutorial, we're going to use this MNIST database, which is kind of the hello world of machine learning. It's a database of handwritten numerals that people use to classify into, obviously, digital numerals. There's 60,000 handwritten digits, and the best record is about 0.21% error. We're not going to hit that today, obviously, but people have used this over and over for sort of a benchmark of how good is your algorithm and how good is your model at Oh, okay, that's awesome. Some more caveats. Make sure that your data set is something that you really want to use machine learning for. Trying to do NLP with machine learning is a bad idea. It's a hard problem. You might kill your computer. It's also a good idea to know machine learning theory before you just download the MATLAB toolbox or whatever free toolboxes you can find online and just shoving data into it. Because you might be hitting some of these warning things that we previously mentioned and you just don't know it. You don't know that your data set is not appropriate until you try to publish it or do a presentation on it, and then somebody points out, do you know what you're doing? Are you sure? And then as Cal already said, sometimes machine learning models lack interpretability. So think about what you're actually trying to get out of it before you start messing around.
Okay, so in the spirit of not doing something without knowing how to do it, or what it's doing, we're going to do a quick crash course into what artificial neural networks are actually doing behind the scenes, so that if you use them, you sort of know what it's doing, and then you can maybe look at the network and try to figure out why you're getting a certain output versus another. So artificial neural networks are inspired by the brain. They're not exactly like the brain, because the brain comes to work as dynamical systems, whereas these just sort of sum the values that they get and then output some value. Each neuron, so you can see the network, this is sort of a very simple network. It's composed of layers. If you just have one layer that connects to one output neuron, that's called a perceptron. And those have been around for a long time. And it took advances in algorithms to get to the point where we could learn on multiple layers in the network. But generally, you'll have an input layer. So for example, in your image, the input layer is going to be the pixel values that you want to train on. So for a grayscale image, you might see something like 255, 0, 135, 64. That's getting fed into each input neuron in the network. And then the output neuron is the class. So all machine learning right now does classification. That was sort of what Kelsey talked on. It tells you, is something this or is something this? So maybe if you're in environmental sciences, you want to know, like, is the temperature going to be above this or below this? Like, is there a storm, is there not a storm? So you can sort of use your imagination. There's a lot of different things you can sort of say, is it this or this? That makes machine learning so powerful for a lot of different applications. So I put one hot vector. So generally, if you have something that you're trying to say, is something this, 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 or this, you have to predefine what the output you want to be. So you'll say something like, you beforehand will assign each one of these positions to be the value that corresponds to the class that you want. So you'll say, okay, well, this means apple, and this means banana. Let's say we're taking. Okay. So when you do supervised training, you're going to feed it in the correct label according to the one that you want it to be. So if I feed it in a picture of an apple as the correct label, I'm going to give it this vector, because I know that the one all the way to the left means apple. And then when I feed it in a banana, I'm going to feed it in the one in this position and put that to be a 0. Okay, so what happens is, at the beginning, the whole network is going to be random, because we don't know, the network doesn't know anything yet. So it starts off with random weights, and it's going to, you're going to feed in the image, all, 600 by 600 pixels, so there's going to be a lot of pixels. We'll get into what the two-dimensional version of this is in a second. But it's going to, each connection has a weight, so it's going to multiply the pixel value by the weight and add that into the receiving neuron. So each receiving neuron is going to add up the weight times the intensity value from all the receiving input layer. And then that's going to pass it through about a sigmoid or a ReLU, which we'll talk about in a second, which will either look like this. We'll actually have a picture. That sum will get passed in to one of these functions, which bounds the value between either 0, which either makes 0 the minimum or saturates the value at some point. So at the end, this process continues on and on. So this value that comes out of the sigmoid is then multiplied times the weight of the receiving one, and the same thing continues. So instead of the input pixel value being multiplied by the weight, it's the value of the sigmoid for the middle layer, and then all the middle layers after that. So at the end, you're going to get like something. Let's say you gave it a picture of an apple, and you wanted it to be 1, 0, 0, 0, because you want the thing to learn that to output a 1 when you give it the picture of an apple. You're going to get something like or something like that. You're going to get some random garbage. Because the network has random weights, you gave it a picture, and the random weights times the picture are going to give you something that's completely different from the 1, 0, 0, 0 that you wanted. So the magic of the neural network is it takes, so you then take this vector, you basically find the difference between what you got and what this vector is, and it applies changes to the weights backward through the network that tries to make it so that when you get this input again, it moves it closer to the 1, 0, 0, 0. Okay? Are there any questions about this? Okay. Okay, so again, this is a basic one-dimensional neural network. So you have a one-dimensional vector of inputs. It's summing up to each middle layer from the inputs of each input layer. And then it's getting passed into one of these. So these are 4 different, so we'll see in Keras you have a choice of what kind of activation function these are called to use in your network. A really popular one is this, I'm sorry if it's not really super clear, but it's the blue one that goes like this. It's called a ReLU, a rectified linear unit. It basically says any input that's negative, so if the sum is less than 0, the neuron outputs 0. And if it's greater than 0, it outputs whatever the value that it outputs. So the other ones are, if it's anything less than 0, you can see it will shrink the value to something that sort of bounds it between these two. And you can sort of think if you're like from bio field, you can sort of think of this as like a firing rate, because the neuron can't actually fire infinitely. So at some point, the neuron just can't fire any faster than it can, than some limit. Okay. Am I doing fine?
I think it was 0.5, not 0. Isn't that right?
For what?
If it's less than 0.5, it goes to 0. 0.5 goes to 1.
Well, for
It depends on the function.
it depends on the function. You can make it do that. I think for the standard rectified linear unit, you can see here it's anything less than 0 goes to 0. But yeah, you can move that line, and you can tweak all these functions.
We'll actually get to that later, that you can select which functions you want to use when you construct these networks.
And you can see the soft plus, the green one, is similar to a rectified linear unit, except it tries to mimic the shape, but it's continuously differentiable because there's no kink in the. Okay, so as Kelsey said, like the earlier kinds of machine learning were when you had to handcraft features. So you had to detect corners, like corners, lines. There's a thing called SIP features, which have sort of died away because of deep learning. You had to like run these algorithms on your picture. It would then detect all the corners you have, and then you would then take these corners as features and pass them into like a one-dimensional artificial neural network, or an SVM if you've heard of those. But Jan LeCun and the others pioneering convolutional neural networks said, why don't we just add the feature detector before the artificial neural network, and then have it backpropagate through the features, so it actually learns the features that it needs to find while it's training to say whether it's an apple or an orange. So that's the core of convolutional neural networks. It's learning the feature detector while it's also learning the network that classifies apple or orange. So here we can see the very standard picture of what a typical CNN architecture is. So instead of having a one-dimensional input for the network, so you can see here is the network we just saw, where you have one-dimensional neurons connected. But here we have now two-dimensional neurons connected, which is the same thing as the one-dimensional. So also the two-dimensional is getting fed forward into another two-dimensional in the same way. It's just you have to think of it like it's in 2 dimensions. So when the algorithm backpropagates to say whether this was right or wrong, it actually sends it to a 2-dimensional plane rather than a 1-dimensional line. And then when you get to this point, you can see it says flatten, because you can't actually connect this 2-dimensional to a 1-dimensional thing. So you just take the 2 dimensions and you like stretch it out, right, into 1 dimension, and then you connect that to the 1-dimensional line. So what are these words here? A convolution is a matrix, so it's an n by n matrix that you put over the image, and you multiply every associated pixel that it's covering with the value of the filter. So you say this times this, this times this, this times this, this times this, and you go like this, and then you add them all together. So for every pixel value, you sort of shift this window over the image, and you multiply the corresponding values, and then you get one value. So at the end, you'll still get the same number of values as the image has, except it will be transformed by this filter that you've been shifting over. So here we have 32 filters that it's learning, that it's shifting over, but it's also learning via the backpropagation algorithm from the deep learning. And max pooling is to reduce the size of the network. So you take the most salient features that you get from that you've learned, and you pick the maximum value. This has just been proven to show that this actually works really well. Okay.
All right, so we've gone over a lot of the theory and background of all of this, but now, because as people have known for 1,000 years, people hear and immediately forget, so now we're actually going to give you a bit of a hands-on application again through Keras, which is a wrapper for the Tensorflow toolbox in Python. And I should point out that although Keras is in fact simpler and easier to use than Python, than TensorFlow, it is not actually easy. So anytime you start having issues with let's just let any of us know. But yeah, so for those of you that got this in the email, you may have already gotten the instructions for getting into the shared folder for this, which includes both a Python notebook that will contain all the code that we're actually going to go over bit by bit in this tutorial here. But if you want to start downloading that now and open it in Colab, you'll be able to run this yourself and kind of play around with it a bit and get an understanding of what is actually going on that we've been talking about here. So I think we have, yeah, so the everything should be at the tiny URL link. Let me or anyone know if there's any issues with opening anything. But so as you open the code, you'll see it at the beginning, just this whole chunk of code about importing different functions. Particularly first importing the print function there, don't worry about that. That's just a Python thing of getting one of the features of Python 2 into Python 3, right?
Yes.
Or the other way around. Yeah, this is just for convenience later on. And then next you'll see that we're importing the Keras toolbox there, and then particularly importing the dense and flatten, con2d, and max pooling operations that Matt was just talking about separately. So we'll just be able to call those without having to keep specifying that we want specifically the Keras version of those.
Felix.
Do you want us to follow with you, or to do it on the spot, or to just pay attention to what you're saying?
For now, I would say pay attention to this, but if you want to kind of look along what each line means, you can. Maybe don't distract yourself trying to figure things out because we will have time to go in depth in this after going through these things bit by bit. So if you feel like you're lagging behind a bit, don't worry about it too much. But yeah, see what you can get around. And this code is very modular, which is nice. So there will be plenty of opportunities to catch up if that's an issue.
Do we need to connect the internet when we,
you can do it offline if you already have Colab, or if you have anything that can open a Jupyter notebook in Python. Otherwise,
yeah, and if you have Keras downloaded, you can do this offline also. You just have to install. If you've installed the packages for Keras, you can do this on your own computer. This is just so that people who have installed nothing can follow along with us here.
Yeah, so that's just a standardization thing. And also, in the folder, there is a useful links document which actually goes over all the steps that you need to install all of these things, so you can actually play around with these things in depth on your own time and apply things to your own project. But so once all of the functions have been imported here, we're then going to actually import the MNIST dataset that Kelsey was talking about of these thousands and thousands of handwritten digits. And that's done with this particular syntax, just calling the MNIST tool set and loading in the data. We have to go for this particular syntax here to load out the training and test data sets that will be used for cross-validation, so we're not overfitting when you're actually running these things. And then we need to start specifying the actual dimensions of these things so we can reshape them and tell the network what kind of operations it needs to do so it can transform them from the 2D images into 1D vectors like Matt was talking about, which it basically does by just picking each row and kind of appending them to one another. And in this case, you can see that these images are 28 by 28 pixels. They are grayscale, so there's only a single color channel that just represents plain luminance. If this were an RGB image, instead of the image columns, image rows 1, you would probably have a 3 here. Again, input that at the back here. This is just another way of reshaping this data, particularly for the format that Keras wants. If you're using a different toolbox, you will have to do a different operation, and there will be plenty of documentation telling you what exactly you actually need to do to get it, to arrange the data, and of course it also depends on what kind of data you're actually interested in classifying or training with. In this case, we just have these 28 by 28 pixel images with a single luminance channel. So all we need to tell Keras is what the overall sample number of each is, which is just a continuous vector linearly increasing from 0 to the number of samples. And then finally, because this data is in fact compressed, we need to change the data type to a float 32. This is a really common issue for anyone loading in their own data for the first time and then wondering why the hell nothing is working. Change if there's any kind of compression that might be messing you up, because most programmers disregard this problem entirely and don't have a tailored error message for it. So it's a surprisingly common thing. And finally, we just normalize the luminance to being bounded by 0 and 1 from 256 levels. And finally, this is where that print function comes in to just show, as you're actually running the code, that everything was processed correctly. And so then we actually define the number of classes. Now, obviously, these are just single digits from 0 through 9, so we only have 10 classes total. And if we want to define, let's say, the digit 4 here as representing one of these images, this is one of those one-hot vectors that Matt was talking about earlier. It's essentially just a dummy variable that indicates what exactly the network is supposed to learn as you're training it, and then what it's supposed to output when you're actually testing what it's capable of doing.
Just to add it, you can interpret it as a probability. So the 1 will mean like a 100% chance that this is the object, because you won't ever end up with 0.001 when you actually run on real world data. You'll get like 0.1, 0.1, 0.1, like some high number.
As the output.
As the output, right, sorry, as the output for when you've trained your network. You'll get like a higher number for the one that you wanted, so you won't get zeros and ones, but then it's the higher probability one that you can say, okay, this is the class that I'm looking at.
All right. Okay, so, thanks, Felix. So this is the network that we're going to construct. It's the one that we were looking at earlier. It's a fairly standard sort of model that's used for image recognition. We're going to build it in 3 pieces. So we're going to have 2 chunks in the convolution and pooling, as Matt described, and then feed that into a fully connected neural network at the end that can provide us the output that indicates the confidence, probability, or likelihood of the class labels, depending on how you'd like to think about it. So first we construct this sequential model. The sequential model is a feed-forward model, so we're going to stack a linear collection of layers, and they're going to feed one into the next. So this first line here is constructing the convolutional layer that Matt described, and we're going to build it with 32 kernels. So these are the convolved kernels that Matt was talking about that we're going to learn during training. There's a couple of parameters here that we can select. Here's an image of what this sort of looks like. So we're going to use 5 by 5 kernels. This image has a 3 by 3 kernel. But you can kind of see how these operations work, where we have a sliding window over the image, and we perform this operation and get an output. And then we perform the pooling operation. So the way that you can think about this is that if we detect a feature in a position on the image or 1 or 2 pixels over, it doesn't really matter for classification of the image. So this allows us to actually downsample the data and decrease the number of parameters in the model. So you can see this example of 4 by 4 gets downsampled to 2 by 2, which speeds up training, because like I said, it reduces the number of parameters. Another parameter here for constructing this layer is selecting the activation function like we were talking about before. In this case, we're going to use the ReLU activation function, which is the leaky ReLU in Keras. So it looks like this. So the difference between this and the typical ReLU is that we have this leaky factor down here. I'm not going to go really into the theory about why that's a useful activation function, but you should know that it's a pretty common one. And then next we add the max pooling layer here, and the pool size is 2 by 2.
Just a general question.
Yes.
Are the kernels learned as well?
Yes, yeah. So the idea here is that, Matt was saying this is what we expect and this is what we get. And the backpropagation process passes errors all the way back through all the layers, terminating in those original kernels. So the entire thing is randomized, and then it ends up learning which features are actually relevant for classification.
Yeah, that's one of the beauties of CNNs, was that now it learns the kernels in addition to learning the last layers where it's just one-dimensional.
Yeah, so you could think of these kernels as, say, edge detectors or corner detectors of a 5 by 5 pixel region of an image. And that's also referred to as a receptive field. And then we're going to construct this max pooling layer. Like I said, the pool size is 2 by 2 and the stride is 2 by 2, and that's exactly what's shown in this image here. So you can sort of think of it as another convolution, but really you're not performing the same operation. You're just taking a max over a region. So then we're essentially saying we don't care exactly where this feature was found. If it was found in this small region, we just pass that information forward. Then we're going to add the second convolutional and max pooling layers, which is essentially the same thing as the prior one. But now we have a downsample input. So if you notice before here, we had 28 by 28 coming in. But because of that stride of 2 in the max pooling layer, we now have an output of 14 by 14, and then 1 for every kernel that we've learned. So that's what's coming in here. So we repeat this process, but this time we're going to use 64 kernels. So now we are performing operations on the output of the prior part of the model. So we're looking for correlations between the low-level features that were detected by the first part of the network. So you can think of it very similarly. We're performing a convolution over the detection of low-level features in the image, if that makes sense. And again, we're going to do this pooling with a stride of 2, and we're going to end up with an output of 7 by 7 with 64 features. Question?
Sorry, can you just repeat, what does strides here do?
Yeah. So the stride affects how much the filter is shifted for each cell. So in this example here, if we had a stride of 1, then when we compute this cell, we would shift this kernel over 1 pixel. If we had a stride of 2, we would shift it by 2. So you can see that the stride determines the size of the end layer. So you have a stride of 2, the layer is going to get cut down by a half. And that's what we end up with here with the pooling. So you can have stride in either one of these steps. It's fairly common to do that with the pooling layer, though.
And in the X and Y direction separately?
Yeah. So, yeah, that's part of that is you can make these kernels non-square. You can make the stride different in the 2-dimension. It's kind of hard to determine under what particular circumstances you would want to do that, and that's part of the idea of learning machine learning is understanding how these parameters affect the performance of the model and how to select which ones. Yes. Okay. So now we have this output, which is 7 by 7 by 64. You could think of this as a map of where feature correlations exist in the image. And at this point, we are essentially discarding the spatial relationships between them because we're not going to do any more convolutions. And so that was the flattening step that Matt mentioned here. So we're going to flatten that out into one layer of 3,164 nodes. And that's a very simple call of adding that flattened layer. Then what we're going to do is build this classic sort of one-dimensional neural network thing where we add a hidden layer. So we're going to stack this dense layer. By dense, what's meant is that every node in this layer connects to every node in this one. So we're going to get a total of, 3,164,000 weights between the two of those. It sounds like a lot, but it can get pretty ridiculous pretty quickly. And again, we're going to use this ReLU activation function. Finally, what we want for the output is this vector of probabilities or likelihoods or confidences for each label. So what we want is to put the image in and have it indicate to us how confident it is that this image is a 1 or a 3, for example. And so for this, we use this softmax activation function. This normalizes the output so they sum to 1. So then you can sort of interpret them as probabilities and train with these 1 hot vectors because no output's going to be greater than 1. And we pass in the number of classes there to tell it how many neurons are in the output layer. This is a visual depiction of that flatten process, just so you can see what that looks like. Okay, so now that we have the network set up, we have the infrastructure in place, we have to compile the model. And compiling the model prepares it for training by indicating how we're going to compute the loss and how we're going to optimize during training. In this case, we're going to use categorical cross-entropy, function over there. And this is going to drive this process of moving the output vectors towards what we indicate that we'd like. And so this is sort of the heart of this whole process is the network says, well, this is what I thought and this is what you told me, and then it backpropagates those errors to compute the gradient for every weight. It determines how to change that weight in order to get closer to what you told it you wanted. And that's a whole other thing that we're not going to go into too much detail on. But yes, and then the other component here is the optimizer. Another thing I'm not going to go into detail in, but the Atom optimizer is extremely popular in Keras. And it essentially uses adaptive learning rates for all of the parameters. And it speeds up the rate of convergence for training the model. Finally, we're going to collect information about accuracy, and that's going to be programmatically available to us after we do the training. And here's the call for training. You can see this is kind of like neural net Legos. You know, we build the layers on top of it, and then we compile it and run it. The library makes it very easy to do these sorts of things. You just have to indicate the parameters, and there can be a lot of them. In this case, for training, we're going to pass in the X train and Y train. That's all the training images and all of the 1 hot vectors that we constructed that correspond to which digit they are. We're going to run for 10 epochs. An epoch is one pass through all of the training data. In this case, we have 60,000 images. So it's going to run through all 60,000 images, and it's going to adjust the weights as it goes. We're going to do batch training, which is where you run the network with multiple images and collect those gradients, and you do an update at the end of that batch. That's just sort of a minor detail. You could update after every image presentation, but this is just another common thing that people do in machine learning.
Can I just add a point about the X train and Y train, are going to be vectors, and every position of the vector is going to be the same in both. So in one, you're going to have like image of apple, and then in the same position in Y train, you're going to have the 1 hot vector that has the 1 where the apple is. And then like for banana, you're going to have the 1 where you want. So the images and the hot vectors are exactly in the same positions. Otherwise, it doesn't know like what to map to what.
Yeah, and that's the first dimension of that 4-dimensional matrix that we constructed from the training data. The first dimension was which sample, and then the second and third were the image themselves, and then the fourth was the number of channels. So the Y train is organized similarly, where you can index in the first dimension for each sample. So yeah, that was batch size and epochs. The verbose just gives us this lovely output as we train, so we can see what's going on instead of just having the pinwheel go for like 10 minutes. And then finally, we provide this validation data, which is the remaining, how many was that? I can't remember, 10,000 or something like that, images that are used to compute the accuracy as you go. You don't want to compute the accuracy based on the training data itself, because then you get overfitting. So in this case, we want to train on one set of data and validate it by looking at images the network has never learned from as an indication of how well it's actually learning the task and not just memorizing the data. So for that, we pass in this validation data, which is organized similarly. And so you can see here, MNIST is basically a solved problem in machine learning, which is why we hit 98.73% accuracy after 1 epoch. But you can sort of squeeze more gains out of it by running further training. So once we've done the training, then we can evaluate the model using that test data. And this will just show us these numbers that were actually here on the bottom layer. 10th epoch. But this goes to show this stuff is programmatically available, so if you were running a lot of different models and you wanted to collect information on their accuracy, you could do that. And to do this, we just pass in the test and the test data, X test and Y test. Pretty straightforward. Okay, so finally, we have this model. What good is it if we don't get to use it for anything? Unless we're just trying to see how well we can perform this task. We might actually want to use it on new data that we don't have labels for. So that's what you can use this predict function for. So what I've done here is I've taken the first 10 of the test data here, passed them through, and collected the output from the final layer. And that output looks something like this. Right? It's run through the softmax, so it adds up to 1. And it's common for people to interpret those as probabilities that the image corresponds to the class. So I printed out here an example, where I printed out here the output for the first 10 images. You can see some of these values are very, very small, e to the -9. But these numbers here are the index of the largest value. And you can use that to determine or assign a digit to each image. So that's sort of like this process here. What you'd like is the index of the correct label to be the highest out of all of them, and then you can use that for classification. Does anybody have any questions? Cool. Kelsey, did you have this slide?
Oh, yeah. Okay, so now what? So you're pretty much set up on your laptop right now to do this with your data set of black and white images, if you happen to have one of those. Felix basically told you that if you have colored images, just make sure that you're set up for colored images is pretty similar. But obviously, the beauty of machine learning is that you're supposed to be able to input lots of different types of things in. And you're showing how to stack your layers so you can try to fiddle around with what it's giving you, or read documentation to try to input other images or other data sets as you like. And I think in the documentation we gave you, there's some stuff about how to import CSV files into Keras. So if you already have data in that kind of format, then you're already started on your way.
So yeah, we have, to be a little more clear about this, the Colaboratory app in Google Drive allows you to run these in the browser without installing anything, which can be an extremely involved process to actually install on your machine. So we've provided a Python notebook that has all the code that we went through, so you can run this step by step. You can modify parameters to the function calls. If you are so inclined, you could pull up other data and modify the network to fit with it. But our goal here is to just have you be able to run it and see it running, and have a piece of code that you understand that you can modify for other tasks if you're interested in doing so.
That's it?
Yeah.
So just to kind of show you, this is the folder we had for you. It has the slides, it has these instructions, it has information that I'm about to tell you right now, essentially. But if you open up this Python notebook, you don't have edit permission, so you can't run it. But you can make a copy in your local drive and locate it and open it up. And if you have the Colaboratory app already, if you've already used it before, it will be in this list. Otherwise, the instructions indicate how you can get it in this list. You click open it in another app.
And it works best with Chrome or Firefox. Safari seems to really complain about this, just as a warning.
Yeah.
What is Tensorflow about? Is it about constructing networks?
So Keras is basically calling TensorFlow functions for you. So to do what we just did it was like an 11 lines of Python would take 64 lines of TensorFlow. So it's really just like it's mapping like a set of commands in TensorFlow into one command in Keras, which has like a trade-off, because when you do that, you lose access to be able to actually unwind the network. But if all you want to do is to like stack a bunch of layers on top of each other and then get an output layer and like train a model, Keras is great because you don't have to, write 6 times the amount of code that you would. But if you really want to get in there and like rewire what TensorFlow is doing, then I would recommend looking into TensorFlow.
It's a good way of setting knobs for you if you're not interested in setting them yourself. But if you get straight, at that lower level, then you have a lot more options. It can be really overwhelming.
And TensorFlow takes care of like a lot of the linear algebra involved in setting these things. That's kind of its contribution, as opposed to just like building them completely from scratch.
It's highly optimized.
Yeah.
Thank Google for that. That's not unusual.
Yeah, there's another one called Tf-Learn that is very similar to Keras. So I would say learn Keras just because there's so much more people using it. Then if you Google an issue in Keras, you'll find people having the same issue, whereas if you do Tf-Learn, you're probably not going to find.
Yeah, so if you're not familiar with IPython notebooks, it's basically breaking up this code into these chunks that can be run independently. But if you're just opening this up and not sure what to do with it, if you go to runtime and run all, it will run all of these chunks of code one at a time and show you the output as it goes. So you can see using TensorFlow backend. Now we're preparing the data. We have this output here. You can see from the print statements. It was 60,000 train samples and 10,000 test samples. Then we constructed the network, and finally we're in the training step. And you can see as it goes, our accuracy is going up and our loss is going down. Like I said, after one epoch, we're going to get pretty close to the ending result, but it's nice to be able to see it. And it's really nice to be able to run this in the browser without having to go through the process of installing all of this stuff. And I believe that there's GPU support for this, but proceed at your own risk.
Yeah, Jesse?
You said that it looks like the accuracy already gets very good pretty quickly, considering, we have like 64 feature maps in the end before we flatten, right? And
yeah.
It's
64 correlations of lower level features, of which there were 32. It's a lot.
It's just to get a sense of how much data is needed. Is there a good rule of thumb in terms of when you guys want to get a sense of how much data you want before you can get to train? Because if you're building up a model, you're choosing how many feature maps at each step, how crude you want it. Do you have is there a good rule of thumb for trying to estimate how complex I should make the model based on the amount of data I have?
Not that I know of. I believe that's an active research area in machine learning, unfortunately.
I think that's why this gets criticized as tinkering a lot, because you just sort of put more data until it becomes more of an engineering thing. Like you're trying to engineer the network to work the best that it can.
Or you pull a Google and you use reinforcement learning to train a neural network to produce hyperparameters for the training of another neural network, which has been done. It's kind of ridiculous.
So they have the benefit of like a very large data set, whereas
the general rule is that your model approaches a ideal state as data approaches infinity.
Good to know.
Yeah.
The other good thing about this, about convolutional neural networks, is since you're using the same kernel for any position in the image, you get a lot more out of the data that you have. If you weren't doing that, then you would have to have examples of certain objects in all sorts of different positions. This is referred to as translational invariance. Convolutional networks can detect features in images regardless of where they're found. So that allows the kernels to be learned from all the positions in the images as opposed to having to learn one kernel for one part of the image.
So it might be more helpful to think also in terms of each data point as having, like if the images are more complex and more detailed, necessarily it's going to train it more quickly. So.
Yeah, you could almost think of every sample being a little window of the image. And so for every image, you have this whole set of data that you're using.
Yeah, when you see something like this that jumps up to 90% from one epoch, it's a statement that the features are not complex. That it's able to do this. It's able to if you that chart that graph we had where you had the line to separate them. It's a sign that the clusters are actually fairly far apart from each other. So the second that you draw some line that sort of somewhat separates them, you're already doing pretty well.
So as a little exercise here, we could go in and say instead of 32 kernels, we could use 16. And then on the second, we could use 32 instead of 64. That'll make the model a lot simpler. And so we can stop this runtime and run it again. So let's see what it looks like now. Still pretty good. We're going to hit probably a similar layer, so level of accuracy here. So, I mean, like I said, MNIST is a solved problem. It's used almost as a sanity check for models. If it can't solve MNIST, there's probably a bug somewhere, at least if you're dealing with image data. But it's a good way to get you on your feet, and it's included in Keras, so you can just import it and not have to deal with actually handling the files and doing any extra data processing. So yeah, it looks like we're basically in the same position here after one epoch. So a fun exercise might be how simple can we make this network and still have it solved MNIST. With a single layer perceptron, you can get in the 80%, which is kind of goes to show. And that's without any convolutions, right? So that would be taking the entire image in and completely disregarding spatial relationships between the pixels.
Yeah, and also you can see now already it's kind of circling whatever the inverse of a drain is, and that it's kind of going up and down around the optimum because it's already doing so well.
Yeah. But it capped out at slightly lower, 98 point something instead of 99 point something. People have competitions for how many fractions of the percent they can increase in the same set. So let's try less. I'm going to go to 8 and 16 and see what happens.
Can you change the sprites to 7 and 5?
Oh yeah, you could. So one thing would be if the stride was larger than the kernel, then you're going to be missing data in the image. So typically you would want it to overlap to some extent. But yeah, absolutely. And that would increase the downsampling, so it would make the model even simpler as well.
Probably wouldn't do that for speed reasons. It wouldn't like make any difference.
Yes.
At what step did you choose the convolution matrix?
I'm sorry?
Did you choose the convolution matrix?
Oh, so that's learned by the model. So all of these 32, or in this case I've reduced it to 8, all of those matrices that are involved are learned by the model itself. So this is a major advantage of convolutional neural networks, was people are feature engineering and saying, well, there's an edge here, and writing algorithms to extract those features, and then McCoon and friends decided that you can do that automatically.
But suppose you wanted to explicitly take care of certain transformations which lead to the same image. For example, the images might be squeezed horizontally, so you know the transformation. So how do you put that in?
That's an interesting question. Do you have an answer for that?
Yeah, I mean then you wouldn't necessarily need a convolutional neural network, because if you
No, you might need it because there might be other correlations that you don't know about, but there is this one thing that you know, that say all the images are either in its original form or they are squeezed horizontally, just to give an example. So you might still need convolutional neural network to take care of correlation.
Holding some of the kernel's constant is the question.
I mean, you could. It would be kind of difficult to do in this library because it kind of pulls you away from the actual lower level details. That's an interesting question, though. Maybe there's a part of the library that lets you indicate, certain seed kernels, for example. Yeah.
Yeah, if you were actually implementing this in base TensorFlow, there are plenty of ways that you can essentially only actually train certain parts of the memory and keep others constant. So if you already have a set of kernels that you just want to apply the convolution to and then learn whatever the image does to those kernels, you can do that.
Yeah, you could also just apply the transformation before you pass it in, right? Because if you know what the transformation is, then you apply the transformation you know, and then just pass it into the deep learning. Therefore, you take care of the transformation you know, and then the network will learn the other transformations. That's the way I would do it. So yeah, you sort of like pre-process the data by transforming it using the convolution that you know already.
I mean, you might not know it exactly. You know that, say, it's
Well, yeah, if you don't know it exactly,
like
then
how much.
if you don't know it exactly, then I would just not do anything and have the network learn, because it will learn the transformation.
Alternatively, I'm sure there's a way to just set the initial state. So if you want to, let's say, start with, I don't know, a PCA, quick PCA or something of your image base and just set that as the starting weights instead of randomly initializing them, that would be one way of approaching that I think would be useful. Might save you some time in the learning process, and you might start at a better position.
I mean, the great but sad thing is it's really powerful. So like you just pass it in, it will learn good feature maps or feature convolutions.
You'd like it to.
Yeah. There are some data sets with tons of local minimum where that might actually be really useful. So it's a good question. I mean, it depends entirely on your data.
So is there any other kinds of data where you can apply convolution neural networks in particular? I mean, besides image data?
I mean, auditory data you might want to go over time on just a single vector and see if there is a particular auditory feature that you're looking for. If you've got some kind of other more complex data, maybe some kind of metadata that you want to look through for instances of a particular pattern.
But yeah, because CNNs were somewhat inspired by the visual pathway in the brain. That's not the only the reason, but like because of its two-dimensional feature, because of the two-dimensional spatial layout, they are heavily used in images. For things like sound data, you can use them, but anything where you have a temporal component, you might want to use like something that incorporates time, like a recurrent neural network or an LSTM or something like that. Or so an LSTM would sort of take data in as it's coming in. You could also do something like with reservoir computing, which does temporal data very well. So there's a lot of So depending on it's helpful to know what machine learning tools you might want to use for what. But if you want like the best image processing, it would be convolutional neural networks, hands down. Yeah.
This is the state of the art for those kinds of tasks. And there's all sorts of other things you can do, like image segmentation, attention type networks that get more complicated. But I mean, I'm nuking this network right now, and it's still working really well. I mean, I reduced the channels to there are eight features each, increase the stride, reduce that layer from 1,000 to 100. You can see how much faster it's training, like 10 times faster, and we're still up into the upper 90s. Again, MNIST is pretty simple, but it just is a demonstration of how powerful these are. Someone have a question?
Yeah. I mean, another example I think actually would be people looking at the performance of athletes and then running things over it. Like people use some of these things for predictions of how well a sports team's going to do.
Yeah, like I tried out a project for NLP because you can convert words into vectors. So I was like, oh, it's a vector, and I have a vector, and I have a bunch of vectors. Why don't I put this into a CNN to see if, because I have a bunch of vectors, makes a two-dimensional matrix, and it was terrible. So that's what Kelsey was saying. NLP is hard. It's hard with NLP. So don't just I don't think you can just throw a CNN at any two-dimensional data and expect it to do as well as with images.
Now that the network is fitted and done, can we plot some of those kernels and see how they look like?
I think you can. Actually, I'm not entirely sure how to do that.
I think we should.
Yeah.
I don't know.
I bet you can.
You definitely can, yeah.
Yeah, I don't see why you wouldn't be able to. It's just that you would be fumbling with quite a few numbers at that point.
There's parameters.
We could look at some of those.
Yeah.
See if they're interpretable.
Yeah, you can do layer dot weights or whatever, or layer dot. You can get one of the kernels out and just print out the values of the one of those kernels, and you'll probably end up with something where it gets lines in the beginning, and then it gets like Kelsey was showing with the faces, where it gets low level features, and then slightly higher level features, and then
Yeah, we didn't import any of the good printing libraries for this example here, so we're not prepared for this, but let's see if this can.
I'm assuming it'd be something like this, where you would actually assign it to a variable
I've
right.
not done
access
it,
it
but
again.
I feel like that might be something that somebody
And then I would imagine this
On the website?
this object
presented that in
has
Combine when we did the paper.
variables that you can
Yeah.
access.
When Jesse did the
Yeah.
I was my favorite thing.
I wasn't expecting that question. It's good thinking. Like what's important for detecting images? I'm sorry, for detecting digits and images.
You probably find those online even, if someone's figured out what kernels are good.
Oh yeah, well that's the other thing is that every time you run it, you're going to get something different. Ideally, it would converge on features that are actually significant. So it would be interesting to, run a lot of different networks and see what they come up with. Anybody else have questions? Has anybody gotten it running and is playing around with it? Awesome. Yeah.
Yeah, so definitely like if anyone is actually interested in using this for your own projects, a time-consuming part of this is data collection and data like manipulation and getting it into the form that Keras wants. So what I did when I was learning Keras, which helps, is if you just print like the data that like for MNIST. So if you just like say print like X train or whatever, it will show you the vector format that it's expecting. And then you just sort of make the vector look like the vector that you want. And then for Y train, you give it the ones and zeros. So like I did a thing where I was like classifying like construction workers on campus when they were building stuff. So I biked around and I took really creepy photos of construction workers while they were working, and I think I'm on a list somewhere. But yeah, so I just printed out the training stuff that they give you and then matched it to that. But it is time consuming because you have to type out like 10000 like 1100001000. But at the end you get your own data that you can use for a classification. Did somebody have a question?
Yeah. So it seems if one is only interested in classifying the digits, there are other properties of the digits which can be utilized. For example, like 8 should be easy to classify because it has 2 holes in it, and 0 and something like 6 and 9 would have 1 hole each and the other. So I'm asking, do you know if there are algorithms which utilize such, I guess, topological properties of the images?
Yeah, so
this might already be doing some of that. I mean, if we keep reducing the number of kernels, then it's going to have to kind of just, the second layer is just going to have to mix and match some of the overarching features. So if we were to then look into the connectivity of this, we might find that a network basically set up this way might just have one kernel that's one blob in the upper half of the thing, and another one might be a lower half. And if it's classifying in 8, it might just have an equal weight to both of them. Whereas a 6 might just have a weight to the bottom and have some kind of higher dimensional weirdness for the lower.
Yeah, it might be doing that, but
your question sort of goes back to sort of the history of computer vision, because in the earlier days of computer vision, the tactic was to do what you're trying to do, because they were trying to manually find features that humans cognitively can see in the number and say, like, this is what we should be looking for. So for faces, for example, one of the earlier face detection was the spring model, where basically we had like, a nose with a mouth and ears, and they had some some leaky term where you could sort of stretch them. So we said, I know if I can find a mouth and a nose and 2 eyes like this, but it sort of died away because when you have people looking in some direction that's not exactly facing, or like what he just drew with a 9 like that, like, there were certain like geometric algorithms called Huff transform you can use that would detect like circles in an image. So you could do a Huff transform to find 2 circles that are within each other and then say that's an 8. So I think what ended up dooming that strategy was the variance in the data that people ended up getting when they tried to apply this like intelligent algorithm that was a good idea, but it didn't work in the real world. So what took over from the CNNs was it was able to learn in like millions of weights, like just the right combination that would find the circle, even if it was like compressed slightly, or if somebody smudged the 8 a little bit. So that's the answer to that question.
Yeah, and stuff like this, they're handwritten digits, so it's like you can't really rely on this link being closed.
Yeah, of course.
But I mean, I agree with you, and I think a lot of people would say that if you can extract useful features, then you should. Yeah. And there's no reason you couldn't add this as an additional input to a layer like that. You can do that sort of thing. But the reason people really like convolutional nets is that they can learn this kind of stuff on their own.
And it's actually kind of sad because like there were so many smart people working on in computer vision. It was very geometric, and people had these really intuitive ideas for how to find like the spring models, and for like face detection, for example. You used to have, it was the Viola-Jones algorithm basically found like it exploited the fact that the color under your eyes was darker than your eye color. So you would use these black and white filters all over your face, like in a hierarchical fashion, to detect faces. And it was like a genius idea, and then all of a sudden, like they came out with deep learning, and it was like immediately better. Like the machine figured out everything for itself, and so that took over.
But those smarter algorithms might be better at extracting features from smaller data sets. For example,
yeah,
probably horribly fail if you have just 10 faces.
Right, but Viola-Jones also failed because for the training they actually had to crop just the face out and feed it in, because it had to look, because everyone's eyes, I assume, are somewhat at the same level. I guess no one has eyes below their mouth, I hope. So so it always knew to look for it always knew that if it applied this black and white filter above at the eyes and below the eyes, that it could find that. So people were like, yes, it can classify them, but only if the camera's looking right at you and you crop out the face, right? Yeah. But I think you're right, because as someone mentioned, like these don't do causality. They just do correlation. So I think, and there's like a lot of people that are arguing now that there's like a limit of machine learning, and currently with backpropagation, I'm one of them, that it only finds like correlations in massive amounts of data. So I think there's a lot of room for new research that you can sort of use higher level concepts to feed down into making the network better.
I also want to make the point about dimensionality reduction. What you're suggesting is essentially, I'm going to take a 28 by 28 image, and I'm going to extract 30 features from it, and now I have a 1 by 30 vector. And dimensionality reduction, you need to investigate the model. So, yeah, thanks for bringing up that. That's a good example of like how you want to understand what the data you have is in the model, and make these sorts of intelligence.
And I think it is important to know how they got to this point from. Like it's not just like this came in a vision to somebody in their sleep. Like first people met features, they used simple machine learning, then neural networks, but they still use the features. Then they put the feature detector in the neural network, and now they're learning to find parameters on the neural network using advanced learning. So it's it's a slow evolution that got to this point. Okay. All right, thanks guys, if that's all.